In this module, we are going to take a deep dive into the definition of convergence. Let me recall the definition as it is presented in most textbooks. Let xn be a sequence and x0 in R be a fixed number. We say xn converges to x not if for each epsilon greater than 0 we can find n epsilon in the natural numbers such that mod xn minus x0 is less than epsilon for all n greater than n epsilon. Okay. Now, the order of the quantifiers in this definition is extremely important. To see this, let's first rewrite this definition in logical symbolism. For each epsilon greater than 0, there exists n epsilon in n such that for all n greater than n epsilon, mod xn minus x0 is less than epsilon. So it is at this point that it might be a good idea to read this symbol as for each. For each epsilon greater than 0, there is n epsilon in n such that for all n greater than n epsilon, mod xn minus x0 is less than epsilon. It doesn't matter how you read the second one. Even if you read it as for all or for each, you are less likely to be misled. But reading the first one as for all can lead to some issues unless you precisely understand what for all means. Okay. Now, it's an interesting exercise now to translate this translation back into the original language, that of English. What is this saying? Well, for each epsilon greater than 0, we can find a natural number n epsilon that depends on epsilon. That's crucial. That depends on epsilon such that whenever n is greater than n epsilon, we have mod xn minus x0 is less than epsilon. So we started off with the definition which was more or less in English. We translated it to logical symbolism. Now we have translated back. So the key point that I want you to take from this is that the choice of n epsilon depends on epsilon. Okay. So in general, smaller the epsilon, greater n epsilon has to be. This is just a general statement. It's not always the case, but in general, you have to choose higher n epsilon whenever epsilon is smaller. Essentially, if epsilon is really small, we have to go further along the sequence so that the terms of the sequence are at max epsilon distance away from the limit. Okay. So you should think of epsilon as setting a target zone. Around the limit. And the role of n epsilon is to ensure that xn, whenever n is greater than n epsilon, is always within the target zone. Okay. Now, the reason why we have chosen to present our definition of limit with a function capital N that depends on epsilon is to highlight the fact that n epsilon crucially depends on epsilon. Furthermore, several proofs will become easier if you treat capital N epsilon as a function of epsilon rather than just a quantity that depends on it. To make the relationship explicit using a function makes our life easier. We will see that when we study many examples of convergent sequences and showing that sequences converge to a particular limit. Now, if we had interchanged the role of epsilon and n epsilon, that is interchange the quantifiers, we will get the following statement. There exists n epsilon such that for all epsilon greater than 0, for all n greater than n epsilon, mod xn minus x naught is less than epsilon. Suppose I interchange for each epsilon greater than 0 and there exists n epsilon, writing there exists n epsilon for all epsilon greater than 0. So we have the same definition. Things go badly wrong. And this I leave it as an exercise for you. Exercise. Show that if quantifiers are exchanged as above, the only convergent sequences are those that are eventually constant. What do I mean by eventually constant? Well, that means eventually constant just means there exists some capital M in natural numbers such that xn is equal to x naught for all n greater than m. After a particular point, the sequence just becomes a constant sequence where that constant is nothing but the limit x naught. Okay, please work out this exercise. Now, so what we are going to do now is, we have seen what convergence xn converges to x naught means in great detail. To even go further in our understanding, we have to first understand what xn does not converge to x naught means. What does this mean? Okay, we have already grappled with this once when we saw that limits are unique. We had to see what it means for xn does not converge to x naught. The best way to do this is to actually just formally negate the definition in logical symbols. What was the definition in logical symbols? It was just for each epsilon greater than 0, there exists n epsilon in natural numbers for all n. Sorry, just a moment, I goofed up. For all n greater than n epsilon, mod xn minus x naught is less than epsilon. This is the definition of xn converges to x naught. Well, we have to negate this. The best way to do it is to keep pushing the negation inside. That's the way to do it. Now, when you first push the negation inside the for each epsilon greater than 0, what we get is there exists epsilon greater than 0, then negation of the rest of the statement. Right? Now you push it inside the statement, the part there exists n epsilon in n. So that will just give you there exists epsilon greater than 0 for all n epsilon in n, then negation of the rest. Okay. Well, what's the next step? Well, that's fairly easy. We just repeat what we have written so far, and we have to change this for each n greater than n epsilon to there exists n greater than n epsilon. Then the final negation goes into mod xn minus x naught greater than epsilon, mod xn minus x naught less than epsilon, the negation of that is mod xn minus x naught is greater than or equal to epsilon. Okay. What is this saying? There is an epsilon greater than 0 such that for all n epsilon in n, there exists some n greater than n epsilon such that mod xn minus x naught is greater than or equal to epsilon. What is this saying? For xn converging to x naught to fail, for some target epsilon, it is not the case that every term in the sequence beyond a particular point is fully contained within the target zone. So that merely says that there is some epsilon, no matter how further along I'm on the sequence, that's what the role of n epsilon is. No matter where I am in n epsilon, there is always some other term greater than n epsilon that spoils the day. So this is what the negation of the definition of xn converging to x naught says. Okay. Now again, it's best to translate back into English. There is an epsilon greater than 0 such that no matter what n epsilon in the natural numbers I choose, there is always a larger natural number n such that mod xn minus x naught is greater than or equal to epsilon. Okay. So this is the negation of the definition of convergence. Now let me give one definition now. Since we saw what is the meaning of xn does not converge to x naught, the next definition is that of divergence. Let xn be a sequence. We say xn diverges if for each x naught in R, xn does not converge to x naught. Okay. No matter what choice of x naught I choose, it is not the case that xn converges to x naught. And I immediately give you an exercise. Write down the definition of divergence in logical symbolism. Now there are many ways by which a sequence could be divergent. One interesting way is how the sequence 1, 2, 3, 4, 5 and so on, which is clearly a divergent sequence, this seems to have a special property that the elements of the sequence get larger and larger. In some sense, this converges to plus infinity. Okay, so it's convenient to have a special terminology for such sequences. So I will introduce another definition. Divergence to plus infinity. We say the sequence xn diverges to infinity, plus infinity. Now I'm going to write down a statement which is going to be very, very similar to the usual definition of convergence. The key thing is we want to capture that the terms of the sequence xn get larger and larger. So what we do is, given any m in the natural numbers, there exists n subscript m in the natural numbers such that xn is greater than m for all n greater than n subscript m. Okay? All this is saying is, if you move sufficiently far away through the sequence, then the terms of the sequence will be larger than m. And this must be true for each m in n. Okay? No matter what fixed natural number I take, after some point in the sequence, the terms of the sequence will be greater than capital M. So this is fairly straightforward now that we have spent quite a lot of time digesting the definition of convergence. Again, some more exercises for you. Show that xn diverges to plus infinity if xn is strictly okay, let me just modify the exercise. Actually not a problem. If 1 by xn converges to 0 and xn greater than 0 for all n. This is not the best statement that you can make, but this is a straightforward exercise to solve to show that a particular sequence xn diverges to plus infinity if xn's are all greater than 0. All you have to do is show 1 by xn converges to 0. This is not the absolute best statement that we can make, but this is a good start. Another exercise for you. Rewrite the definition of divergence to infinity plus infinity using functional notation. Exactly like what we had for the convergence of sequences, where we used a function n of epsilon. Rewrite this definition also using functional notation. Okay? So, this is about divergence to plus infinity. Now, one final version of the definitions above. This definition that I am about to give, I will not expand upon it right away. We will see more about this in the chapter on topology. Let me first give a definition. This is the definition of open ball around a point. Let x be a real number and r greater than 0. The open ball of radius r around x, this is denoted b x comma r. This is by definition equal to the set of all real numbers which are at the max are distant away from the point y. Pictorially, if this is the point x, this will just be the open interval x minus r, x plus r. Why this is called an open ball will become very clear to you in the latest sections on the chapter on topology. Okay. Now, I will not expand upon this definition right now, but I will leave you with one more definition and a final exercise for this definition. Rather, let me just phrase it directly as an exercise. Proposition. This is called the topological version. Topological version of convergence. The sequence xn converges to x0 if and only if for each epsilon greater than 0 we can find n epsilon in the natural numbers such that for all n greater than n epsilon, xn is there in B x naught epsilon, the open ball of radius epsilon centered at x naught. Okay, the open ball of radius epsilon centered at x naught. Proof. Exercise. This is yet another formulation of convergence, and this version of convergence, this version of the definition of convergence will prove to be very interesting and important on in the chapter on topology. This is a course on real analysis, and you have just watched the module titled A Deep Dive into the Definition of Convergence.